Good. Okay, so here we are on the weekend of 1/18/1/19 of 2025. And we are in this fuller explanation book here about, and we're talking about angular topology. And on page 85, there's a graphic. And Richard has been, and I think it's really exciting. Richard has been challenged by the idea of how do you come out of that 90-degree right angle paradigm and shift into a 60-degree and include and or in some way include an observer in as one of the points in the graphic. So here's the here's the chart that we have on page 85, and we were going to start reading
Mhm.
here. This is the Cartesian versus the spherical coordinates. And so the Cartesian are the 90-degree angles expressed above, and and then we're showing how this represents a spherical coordinate if a sphere were going around this plane here. So
Oh,
now
yeah.
you want to talk about
Mm.
your question or your paradigm and the shift you're trying to create here.
Yeah, like if you go to the top diagram,
Okay.
um, that one,
Yeah.
and um, oh, if I can on the left side and the bottom, those three coordinates, 90 degree, if I just sort of covered them up um, or erased them in my mind and just worked with the three on the right. Um, and so then if I connected the height uh, arrow, the top, down to say the width arrow, and then connected the width arrow down to the length arrow, and then connected the length arrow to the height arrow, I've got my um, 4.6 interconnections. Um,
Okay, let's take a second and make sure that um, because I think I can represent this. And instead of just saying um, this arrow and that arrow, let's label them A, B, C, D, and let's see what we can do to
yeah,
come up
okay.
with something. And I'm going to try to, and I'm not going to try, I'm going to follow along the best I can. My computer is a little bit clunky when it comes to some of these graphics. And if I had if I had a new computer, these problems would be solved. I used to be quite clever with this stuff. So here's the graphic. It'll take a second to paste in. There we go.
Yeah,
And now I think you wanted to label this one. Weren't you talking about using the height one?
yeah. So,
All right, we'll call it, what do you want to call this? Shall we call it, we got small a, small b, small
well,
c.
you could just call it A,
Okay, there's capital A.
yeah, and then on the width one, um, it could be B.
Okay, and all of that. So you're talking about, oh, I see what I got to do. Let me think here. Yeah, see, what I got to do is I got to take this guy and I got to make it float. That way I can put numbers and stuff. So we're calling this guy A,
Hmm.
and then we're going, now which one is going to be B?
Well, it could be the one to the right.
So this guy right here, right? So I'll
No,
just
the
stick
other,
a B over here.
no.
Which one?
Well, okay, that's okay. It doesn't matter. It could be that one.
Okay. What other one do we want to label?
Uh, well, then the next one down, make that C.
Okay, so we're going to come down here and make this one C. All right.
Yeah, and then at the intersection where they all are intersecting, um, we could call that one D.
Okay. That's A. And then what we're going to do is we're calling this guy right here D. the point
Yeah.
of intersection. All
Yeah.
right. Hang on, think I can do that. We'll put this here like this, paste that in there. I'll call that a D. And I'm even going to draw a little arrow so that this guy is D. Right?
Yeah.
It's D inter D point of D intersection. Sorry.
Yeah. And so I wanted to call D the observer. Um,
Okay. We're
but
going to
but
call
bef
D the observer.
yeah.
Okay.
And
I'm going to do
and
that.
s-
Keep talking.
and then the connecting would be I want to connect A to B and B to C.
And you want to draw a line that connects A to B.
Yeah, so it connects the top of the two arrows, so the arrow heads. Just draw a line down to
Okay. I think I can do that. I'm going to take this line and go right here. Is that what you're
yeah,
thinking?
yeah, exactly. And then do the same thing B to C.
All right.
Um,
Something like that.
yeah, and then it's
And then you're also taking another line and you're connecting A to C kind of because that makes your tetrahedron,
yeah,
right?
yeah.
All right.
Um,
So let me try and click on that. Hang on. All right. I'm going to double this guy. I'm going to move this up here. I'm going to grab this one here, pull it down here. And I'm going to make it a dotted line, even though it's a little bit off. I'm going to work on it a little bit because more lines. I think I get it from here real fast. Uh, Shape outline. It was the same menu. So
yeah,
we're going to make that a dotted line. Now, in order to make this more readable, we can grab this guy, pull it out here,
yeah, yeah, yeah,
grab this guy, pull it out here.
yeah,
All right, great. And then I can take a line here.
and pull it out. Yeah,
Yeah, I'm going to pull that guy out. There we go. Yeah, I don't mind taking the time doing this. This is kind of fun. In fact, what I'm going to do is I'm going
yeah,
to pick one of these arrow. Oh, I did pick the arrow. Good. So we're going to take this guy, start him here, and go all the way to there. And then we're going to make him
yeah.
fatter. Bam. And we're going to make him black. Bammo. Okay, good. How's
So
that?
that even though it's an irregular tetrahedron, it is tetrahedral. It's it's
That's
got
right.
uh, the ABC or the XYZs, and it's got the D observer located at the intersection.
Right.
And so the observer, you know, the observer looks out and sees the height and the width and the length of something
Right.
in his or her surroundings. And
Correct.
the observer is factored into the graphic, and so you've got the elements of the tetrahedron, not 60-degree angles yet, but certainly um, the four points and the six interconnections.
Exactly.
And I guess, from there, it would be a question of then how do you change those 90-degree angles so they end up in a 60-degree um, angled tetrahedron? But even if you don't do it, it still works for me because now it says the observer is engaged. He's part of the observed, which is the XYZ um, coordinates of height, width, and length.
I'm going to take just a second and make sure that this gets saved as, well, I'll tell you, Richard's 90 degrees. I'm going to go Richard's tetrahedron. And then we'll go 90 degrees to 60 degrees. And we'll say the 90 degree to 60 degree problem.
Challenge.
Good. A challenge, yeah. Yeah, it's not a problem, it's a challenge. I will, I'll make that correction now, and then I'll save it for challenge. Boom, bam. Put this up here. Bam, 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 bam. Okay. Now, why does it have, I mean, because we can imagine these angles any way we want. Right now, if this is 90 degrees to, if A is at 90 degrees to B, and C is at 90 degrees to B, then we've got 90 degrees in here. We've got 90 degrees in here. And I think I can, at the risk
Yeah,
of,
well, I mean,
it
in
won't,
one sense, what we've got is a square with its triangle stabilizers.
yeah,
The edges are not equal. I suppose,
right.
I mean, you could have the height, a height of something that's equal to the width and equal to the length, and that should give you a basic square or cube.
And we're going to say that this to this is going to be 45 degrees at this point. And we'll give that a color. We'll make it,
Oh, right, yeah.
we'll make it kind of orangish. Okay, and we're just going to say that's at 45 degrees. Because I'm concerned about where the
Well,
where the
oh,
60.
yeah.
Go ahead.
Well, I was just going to say from the intersection from D out to like, I mean, C, D, and A are 90 degrees. Um, and A, D, B should be 90 degrees.
Okay, so say that again.
Well,
These are going to represent, these are representing 90-degree angles.
yeah. And and then at the end of B, the arrow end of B,
Right, right.
and the angle to C and to A, they must be 90 degrees too. Um,
Yeah, we can imagine this as being equilateral, even though it's
but they could,
lopsided right now. Yeah,
yeah, they could be less, but this is the whole thing. If you've got a height that's much higher than, say, the width, and and maybe not as long as the length, then, and again, if I'm in a building in a room, I can see that the height is 12 feet and the width is 8 feet and the length is maybe 8 feet too. Um, so I know the the three-dimensional coordinate system that I'm in, and because I'm
yeah.
now an observer in that, when we connect the three end points, then we end up with this um, four dimension instead of three dimension, and we've included the observer with the observed.
Yeah, I wish this
See,
were a 3D model. I wish I could make a 3D model, and then we could
yeah,
actually measure the angles and actually see what's going on, and then we could bend it around to get something
yeah.
that you're looking for.
See, you could draw if we at the end of well, there's two other arrowheads that could have letters to them. So we could
Okay,
have one is E and the other one can be F out at
where
the
do we
ends.
where do we put those?
So out at the end of the two arrows that do not have letters at their ends.
These guys out here?
Yeah. Oh, there's three of them. Yeah, sorry. But
That's okay.
I'm
And what do
mainly
I do?
in,
What do I want to do with them?
well, the the one just if you want to the right of A, make it E,
Okay.
and then the one at down below it, make it F.
But I'll tell you, this is inspiring me to this is inspiring
Yeah.
me to um, spend $300 and get another computer to see if it solves the problem.
And
Okay. Yeah.
so then I don't need to put a letter on the remaining arrow.
Well, it wouldn't
Um,
hurt to do it.
oh, we can
We
do it.
got,
Yeah.
yeah, we'll do it. And we'll call it G. That way, if anybody has any question about it, they don't. What about
Yeah.
poor letter G? Okay, good. Now what?
And then well then we can connect A and E, E and F, and A and F in the same way we did with the others. And we'll be able to connect C and G um, with
C,
G
G,
and
and F to
F,
D as well.
and then
Yeah,
we'll be able to do C and F as well. So
that's right.
we'll end up with three sort of tetrahedral uh, graphics coming off of the XYZ coordinates.
Like that, right?
Uh, yeah, and
I
then
do believe so.
A to E.
Yeah. What would be really cool is if I could color these three different colors,
Yeah,
and then we'd have three different colored tetrahedra.
right.
Are we building something cool here? What are we building? I'm so into the trees, I can't see the forest. What does the forest look like to you?
Well, what we're going to end up with is a hexagon.
Wow, it is.
And in some ways, we're going to end up with the observer inside looking out.
Of all of them,
Yeah,
of all three.
yeah.
Are there three here or are there six here? Because we have everything above the plane and then everything below the plane as well, right?
Yeah, we've got
We actually have four. We've got one tetrahedron here. We've got another tetrahedron here, in which case this would be a solid line. There'd be a solid line comparing C to F at the plane of D, and there'd be a dotted line from C to F at the plane of G. Gee, I wish this were a three-dimensional model so we could actually take a look at all the
yeah,
parts.
because there's one, two, three, four, five, six. Yeah. Um, and
Yeah,
there's see what we've got is well, it is
the
hexagonal.
convex and the concave. Yeah.
Um, it's
If
not
you're
a
from Canada, it's hexagonal. If you're from America, from the US down here, it's a hexagonal. No, that's okay.
hexagonal. Okay.
No, I'm only kidding. I'm only kidding. I'm only kidding. Because when we get in this deep into the thing, who cares about pronunciation? It's just
Yeah,
I'm being a jerk.
but well, and the other thing that's actually what's happening to me right now visually is that I can look at what's called I can look at D and have
You know what? This is an octahedron. I just saw an octahedron. Go ahead. We can look at D and what?
Well, I can look at D and I can draw it out so it's at the corner, outside corner of the shape. Or I can look at it and push it in so that it is actually inside looking out.
Right.
Uh, but
I'm going to do something really weird here because that's just what I do,
one,
is
two,
I do
three.
weird stuff. This is an octahedron because I'm going to stick another one down here because I've got, if I start out, let me get this guy, get him up close. If I start out drawing my lines like this, let me get that guy fatter. And let me make him a kind of a unique color. We'll make him puke green. This is an octahedron because um, I'm connecting, but I'm going to make it more octahedral. Let me bring this up here like this. There's 4 planes. This doesn't go here. This is the vertical axis. There we go. This goes like this. Then this goes like this. So basically what I've done here is I've just put a square on the 2-dimensional plane, on the upper plane, right? And everything
Yeah.
above this is a plus number and everything below this is a negative number. So above it, I can take more lines and I'll duplicate them. And I'm going to bring this over here and bring this up to here. And then I'm going to double it and bring it over here, bring it up to here. And then I'm going to go ahead and double it a couple times, bring it up to here, bring it over here, and grab this guy, bring him up to here, and bring him over there. So there's your pyramid. So you have a pyramid on top and you have a pyramid on the bottom. And I haven't drawn the pyramid on the bottom, but that's an octahedron.
Yeah, that part. Yeah, that would be an octahedron, that's for sure. Yeah.
But if we
Yeah.
took just one segment of this octahedron, we have a tetrahedron here. So we have actually 4 tetrahedra. We actually have 4 tetrahedra here, right? Because if we come back and this is still D, we have D. Let me see, what the heck numbers did we give these? We have A up here. Except the A would be more. I'm going to put them in a box. You see in the pyramid on top, there are actually 4 tetrahedra. Isn't that right? Do you see 4
Yeah.
tetrahedra in the pyramid on the top? Okay, good. Then I don't have to go any further.
Well, but I also see what you've done below is you connected B and E, and you connected what did you connect? Uh, it's already connected.
Yeah. So I'm going to create a bunch of things here. Okay. So this is A. We got A up here at the top. Crap. Got to get rid of the lines and get rid of the fill. Okay. So we got A right there. And then we've got This guy over here is the E.
Yeah.
And then, oops. This guy over here is the F, right?
Right.
And then this guy is the C. So I think I'm gonna just go into debt and get a new computer. All right. And then this guy up here is the B.
Right.
Okay. And again, we're going to say that the observer is in the middle. That is D.
Mm-hmm.
And so we have a pyramid created by four tetrahedra. And the four tetrahedra are A, B, C, D. So oops, let me, A, B, C, D.
Right. And then
And
it's
then we've got, go ahead,
AED. Well, yeah, and then it's AED. Uh, um,
AED,
well, it's it's
EFD,
AEFD.
right
Yeah.
on.
And
And
then
then
it would
it's
be
BAFCD, right?
um
And then it would be ABCD. We got ABCD. We got
and we need
A, we need
we,
ABED.
and we need CDFG.
We need CDF. Where's G? Well, you're now below the horizon. I'm doing everything above the horizon.
Oh, okay.
So
Yeah, yeah,
if
yeah,
we go below the horizon, then we put G down here, we're going to have 8 tetrahedra.
yeah.
It takes 8 tetrahedra to build 1 octahedron. And so now we can replace A with G on all of these things. And as soon as we do that, watch how clever this is. A to G. Bam. Nope. Okay. I just made a global change. So all the age switch to G's and all the configurations stay the same. So we can put this. Oh, I didn't want to change them all. I only want to change half of them. This half I want to change. So now this marks everything above the line. And then this marks everything below the line. We haven't drawn these ones below yet,
Right.
but there they all are. Woo! There they all are. Okay, I'm so into the trees here, Richard. I'm not sure I know what I'm seeing. So is there anything that you will do that, and then we'll do this? So now we can take a look at our two creations. So by building these tetrahedra, we built everything above. So this is all the convex stuff, and down here, there would be another one down here. It would be concave,
Yeah, could be. Yeah. And it
or vice versa, right?
yeah, or as you say,
Because
or just the other half of the octahedron. Yeah.
other half of the octahedron, but one's above the plane and one's below the plane. Like when we look at a pyramid, we're seeing the concave structure up there, but above the pyramid, we look in the air, here's this pyramid sticking up, I'll call it concave. If that's the case, there's a convex one down below, and we ain't
Yeah.
seeing it.
Right.
Yeah,
Yeah.
yeah. And when that shifted, go ahead. Okay, any thoughts?
Well, I
We're
mean,
not switching it. Go ahead.
well, for me, it's like when I look at D in the green model, um,
Yeah,
and I can take D, and if you want, I can pull it out or pull it up.
yeah.
Then I create that three-dimensional pyramid, square-based pyramid. Um, and when I draw if I'm working with the tetrahedron shape, um, then when I draw up D, it, it's let's see, uh, well, one way of drawing up the D is that then you actually see the triangle-based pyramid. Um, but also, I think the way we've been doing it, if I um, I draw
The
up
triangle
D,
bit.
then I'm I'm making the observer sort of at the height, and they kind of, if you want,
Are you
look
saying you're
down.
putting D up to A?
No, no,
You're putting D
just
up
if
to A?
it's like if I can. I mean, it's two-dimensional right now, but if I could visually in my own mind pull D out so that it's three-dimensional, um, then I would have a triangle-based pyramid in the same way that if I pull it out on the BEFC, when you pull it out that way, you end up with a three-dimensional square-based pyramid.
Okay, hold
Uh,
it. If I take E out of here, then all I've got is the triangle-based pyramid, A, B, C, F. And that would be a
that's right. Yeah,
triangle-based pyramid.
yeah,
Okay, by putting E there, I now have a square-based pyramid
yeah.
instead of a triangle-based pyramid.
When
Yeah.
when you connect B and E and C and F that way, yeah, um, yeah. And so, I mean, what it does for me is without having to be a perfect sort of 60-degree angled um, tetrahedron, um, I can see it being, if you want, a regular tetrahedron, depending on what the height, width, and length are, and those are variables in any kind of environment in terms of how high you're looking up, how wide you're looking, and how long the system is. So in that sense, all sort of 3D tetrahedral um, images are irregular tetrahedrons, um,
Yeah.
unless you had something that was sort of equal lengths all the way around. But and irregular tetrahedrons is probably closer to what real life is all about. um,
Yeah.
so as I say, my big question originally was, um, can I use the intersection of the XYZ coordinates as the dot, if you want, or the representation of the observer, who then looks out at A, C, and B, or A, C, and E. Um, and then when you draw the lines, you end up seeing that, well, that's tetrahedral when you have
Yeah. I'm going to
all
say
four things interconnected.
I'm going to say something weird here. If you don't have D as the observer in the green pyramid,
Yeah,
then you wouldn't see this. If D were out here, if D were not inside the pyramid, if D were out here, all D would see at the most would be two faces.
Yeah,
Yeah,
and that actually represents what everybody thought should be the case, and that is D, the observer, should be separate from the observed,
and
uh,
outside of the observed. Yes,
and outside, so it could meet the so-called definition of objective. Uh,
exactly.
and by doing it this way, it shows that you can't separate the observer out of the observed, um,
Yeah.
at least not
If I pull
naturally.
D outside of the inside, D will see one or two faces only.
Yeah.
The only way to see the pyramid is from the inside out.
Yeah, and the other thing that was happening to me was, let me see, let me try draw it here. Well, what was happening to me is that when you pull it out, then um, D ends up having to represent a fifth point, and the fifth point is separate from the four
Yeah,
tetrahedral points. Um,
yeah.
and so I suppose it's
Well,
a
and there's
I was
go
going to
ahead.
say it's a way of showing those diagrams to people and say, tell me in the real world, like here, you're sitting in your room right now, and I'm sitting in my room. Tell me whether or not the diagram that the diagram putting D in the at the at the cross points represents what's happening in each of our rooms. I'm surrounded by my XYZ, and I'm in the room experiencing it, except, I can't see behind me, but I can see, I know I'm in that XYZ coordinate room. You are too. Um, but then if I tried to put the D outside, um, it would be like me getting out of my room and going somewhere else and looking at inside my room from a distance. Um, and that would then make me have 4 points, or not 4 points, 5 points, because I'm going to be looking at the XYZ coordinates, the three of them, but then if I see them interconnected um, with the intersection, there'll be four. And so there's no way that I can represent me as part of the observed, um, or being integrated with, interconnected with the observed. I'm actually going to be able to perpetuate the notion that the observer is separate from the observed.
Well, here's what's interesting to me. As soon as I put down here, I place D outside of F, and D will see only A, C, F, E. But because D is actually seeing A, C, F, E, D has got to be included. We now have a vector, an edge between D and those visible dots. If I put D outside of G, and if it's close enough, all I will see, all D will see is A, C, and F. But
A,
because D, what's that? A, C, and F. If I put G really
yeah,
close.
right, right.
So if I put G really close, then G will see A, C, and F. I need it. Oh, okay. If I put D outside F, yeah, but D is still part of that. So if in order for A to see D, D's got to be part of the equation. There's got
Yeah,
to be an edge between D and A and an edge between,
right.
and so we have a tetrahedron right here. No, we have one, two, three, four. Yeah, we got a tetrahedron right there.
Hmm.
And um, in this regard, we have something different than a tetrahedron. What I have is it's a five-pointed thing that's really weird looking. I was going to say obtuse because an obtuse triangle is one with a
Yeah,
where
well,
one of the angles is more than 90 degrees. Right? This becomes a this becomes a it becomes a weird cube. This is some kind of a cube.
yeah,
So
and
you may be,
normally if you go from 4 to 5 geometrically, then what you end up doing is creating a pentagon.
and how would I go
Uh,
to five?
well, if the idea if D
Oh, I see. Here we go.
is
That
pulled
becomes a
out,
pentagon.
well, anything with 5 would end up with a as a pentagon shape. Um,
Well, pentagon is a two-dimensional thing. We're talking a 3D thing. So it would be uh, if we let me see, I've got this picture up here in the way, but if we put D outside here, where do I if I put D outside here, and just for the heck of it, we'll just connect them to that line. I'm going to grab, and I'm going to change this to some color that's more, so with this guy up here connecting to this guy, who is also connecting to this guy, and who is also connecting to this guy. That is there's one side, two sides. This is probably EDCF. That'd be on one plane. So that would be a weird arrowhead.
hmm.
So we have an arrowhead here, we'd have a triangle here, and we'd have a triangle there. I wish this were a 3D modeler and I could just detach that and spin it around and look at it.
Yeah.
But I don't know if you're seeing what I'm seeing here when I stuck those blue things there.
Mhm.
So, but this is your kind of thing. So where do we want to go from here? What do we want to try next, Richard? What do you see next? Or is anything helpful at this point?
Well, I mean, my original question was whether or not I could use the
Or do you want to
intersection
just dream about this for a while and see where it goes?
as D, and the dialogue that we've had says uh, that's possible. Uh, um, but I can't. um I'd have to. I have to do something with the 90-degree coordinates, the out of D to turn it into kind of a equilateral um, same edge tetrahedron. And you see, somehow or another, the 90 degrees have to um, kind of angle in. This is back to this angular topology. They have to angle in so that there's 60 degree connections between all four.
He's not there.
Here you are, Richard.
Told me you had left.
Well, my computer shut down. I'm sure it's lack of resources.
Oh, okay.
Put that on mute. Just touch it, and then there's a microphone in the bottom left-hand corner.
It's muted.
Okay, hang on just 1 second. It is muted.
Mhm.
Why am I? Oh, mute the television.
Huh?
Mute the
Yeah.
television. The mute button's in the middle. Okay. I still got the echo. So I don't
Oh.
know what's going on. I'm going to go back in and show you this chart though. Did you get any ideas?
No, I mean, the main idea, I can keep the, for me, I can keep the right angled coordinates and put the observer in
Put on your headphones.
at the
I
intersection.
have the headphones.
Hang on just 1 second, Richard. I got
Yeah.
a technical problem.
Yeah.
Okay. Wow. This is weird. I have a huge echo. You can hear though now. Okay, good. All right. What were you saying?
Well, I was just saying the main thing for me was
Can't hear.
that I could take the intersection and call it D as the observer,
Yeah.
and I can then connect to the endpoints of the XYZ coordinate system. And I've created a irregular tetrahedron, but I have created the observer as part of the observed. And the observed, of course, it's like saying that if if you were sitting on I don't know, the step ladder at the height of the room, um, then I would be part of your 90-degree angle system. Or if you were sitting at the length end of the room or the width end of the room, uh, then I would be part of your 3D system. Um, and and that's what I've been struggling with as to whether or not I can insert the observer into the XYZ coordinate system and not be misusing the principle of creating a four-dimensional observer observed image or diagram. Yeah, that was the challenge. I think we've demonstrated that it's possible. Then it, in a sense, back to you to sort of say, is that what you think we've done? Is that a legitimate way to get the observer into the observed?
The echo went away, which is weird. The other thing that comes up for me, Richard, is if we take this F here, are you able to hear me, Richard?
Yeah.
Okay, good. If we take F and move F back onto the plane with E and C, so F now takes position where D would have been.
Mm-hmm.
Suddenly, this line from E to C goes straight, and we now have a tetrahedron. The only reason why we have different than a tetrahedron is because F is out here creating this little aerospace. If this pull is pulled back here, we have a tetrahedron because F is only there. As long as F is there, we have 5 points. But when F goes
Mm-hmm.
back on the same plane with E and C, it basically F will disappear until we grab it and pull it out again. And so
Mm-hmm.
we then have a tetrahedron. And I think that it's a cube. Yeah, it is a cube. ACF 1, 2,
Oh
3,
yeah,
4, 5. It's a weird cube. It's a misshaped cube. Anyway,
yeah.
that
And
blew my
actually,
brain out.
when you look over to the left side there, you can actually
Yeah.
see the cube.
Yes. Of course, in a way, because I can also see a hexagon. This is kind of like
Yeah, yeah,
the trick of Metatron's cube. You know what Metatron's cube is?
sort of. I've
Metatron's cube. This is Metatron's cube. I should have stuck with the other one. Yeah, here's Metatron's cube.
yeah,
If
yeah,
I look at Metatron's cube, I can see the cube, but I can
yeah.
also see a double tetrahedron, you know,
And you see the hexagon.
and I see the hexagon if I put it on a two-dimensional plane. In order to
Yeah.
see the cube, I've got to put it on 3D. So it
Either
looks like a
that or you
hexagon on 2D. Go
see
ahead.
what my eye is able to do now is that I can look just about where you've got the little cursor, just to the
Yeah.
point, just to the left of it. I can look at that point and I can draw it out. And
Yes.
so
Bring it out.
it creates the square base pyramid for me. Um, or I can draw
Well,
it
if you
out and then I can see the cube.
and then I can see the cube. Exactly right.
So it
Yeah.
really is an exercise in what the eye can do in terms of whether it can see three-dimensionally on a two-dimensional plane.
Exactly right.
Um,
And think what we
and
could do if we could actually see in 4 dimensions.
Yeah.
Yeah. And of course, the brain can't do that. The brain takes 2 dimensions and creates 4D out of it. Is there any place else you want to go with this?
No, this has been really valuable because it's given us sort of um, a dialogue time, sort of a two-person dialogue time to really kind of go through the exercise and if there was more of us, it really is taking up time that somebody else may not be as interested in.
That's right. Exactly right. Yeah,
And
I
so
totally agree.
so the opportunity every once in a while to be on a in a binary, if you want, or two-person
Yeah.
dialogue
Private consultation, a
is
dyad. Yeah, a dyad. We're in a dyad over here. We're in a
that's
small
yeah,
group.
right.
Yeah,
Yeah.
cool. I
Yeah,
wish I
that
had a 3D modeler. It'd been so fun to build these in 3D and then take them apart and look at them.
yeah.
All right.
Um,
Well, I'm going to send this to you just for the halibut, and I'll also do the recording, send the recording to you.
mhm.
And if you, I think I'll go ahead and put it on YouTube. I'll put it on our Wednesday thing, so it's private, and only the people who get the link can do it, and only you and I will have the link. And if you want to share it with anybody, they will have the link, and they can
Oh,
look at it and
right.
watch what we did. Okay, cool. Anything else before I turn off this video? Before I
No, no,
shut down the share? Okay, good.
um,
Cool.
no, I really
In the
value this.
recording, all of our, go ahead.
I just say I really value this continuation of what the chapter was calling angular topology, and
Yeah.
uh,
And I want to point out angular topology and the point that chapter's trying to make. If we go back to this original guy, right? Um, oh, I shut it down. This was the top one. If we go to the bottom one, let me see here. They're talking about they're um, Edmondson is talking about angular topology, and she starts talking about spherical representations. And of course, the whole time we stayed in, um, we didn't talk about spherical at all.
no, and for me, the spherical modeling is when you can take um, a triangle-based tetrahedron, um, and you have the three upright edges, the 60-degree angle edges, and the bottom triangle. And then when you push out the bottom um, edges into a curve, uh, you end up creating a circle. And once you've created the circle and you add more edges from the top, if you want, or from the bottom, in between the original three, you end up with the indigenous teepee. and
Yeah.
and the teepee is, in that sense, built on a circle, um, although it really is tetrahedral. But when you push out the edges into a spherical shape, um, you get the circle base. Then you can push out the upright edges if you could do it. Um, it's almost like taking the willow straight pole and curving it, and
Right.
you would end up with a dome.
Yeah, well, that's what a sweat lodge is. It's
Yeah,
that dome.
exactly. Yeah.
Yeah. Now, see,
Um,
here's the problem for me is that I think she's trying to build a spherical plane here on the 2 dimensions, showing this being the out direction and this being the in direction, in order to be Bucky politically correct, I would normally say up and down. And I think
Mhm.
that she's saying if she builds these all the way around, she's going to have a spherical circle here. I get
Right.
confused because I see the 90 over here and I see this immediately as going up on the vertical axis, but she's not going up on a vertical. She's staying on the plane and going around in
Right.
circles.
Yeah.
Yeah,
Um, yeah, in that sense too, she ends up with a circle base.
right.
And then if you then you can put your upright edges. You can start with three, and then what I was learning a while back with the teepee construction, then if you put four more poles in between each of the three,
Right.
um, you end up with 15 poles. The
Uh-huh.
original three plus 12 more.
Right. And those 12 are adjusted to be more spherical, where the first
Yeah.
three are tetrahedral right off the bat.
Yes, exactly.
Yeah.
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 Yeah. And then the 12 allow you to get that circle base. Um, so I mean, you probably know more about this than a lot of people, but it's like what what was in the mind of the, if you want, the original TP
TB builder?
constructors.
Yes.
Yeah, that sort of said if we put three pole upright poles in an angle 60 degrees, they may not even known it was 60 at that point, and
Right.
uh, and then if we want to make it round or circular, we put four poles between each of those three because that then pushes it out. um, and so bingo, there it is, a circle-based tetrahedron.
Well,
Um,
and then I'm going to be really weird on you, and maybe you've already thought of this, but if I take three poles to create a tetrahedron, then I take 12 poles and I create a circle around the tetrahedron. Um, a circle around the tetrahedron, I have the Trinity and the 12 apostles.
oh, yes. Well,
So, so anyway, and now
and
I'm
yeah, and
really
again,
getting,
all I'm trying to
they're
say
going to put
is
me
that
in.
uh, the mindset whenever this was sort of this kind of construction was figured out or created, um, what was the mindset, if you want, that allowed that to surface as the, whoa, I think this is the way to build a structure, and one that we can live in, as opposed to trying to build something that was right angled and square and boxy.
I'll tell you, I think that down deep inside, each of us know about the triangle. We know
Hmm.
about the tetrahedron, and I think we know about the 12 principles. I think that hell, they could have settled on 14. They could have settled on 10, but they didn't. They settled on 12.
Hmm.
So I'm kind of magical. I think we came from a place where we knew there was an intelligent design. and we
Yeah.
and we're projecting it and we're projecting it everywhere we go, you know.
Yeah, and then this gets us back to Bucky's sore point about once we once we put that sort of native understanding, natural
Right.
understanding into a school
Right.
system,
Yeah.
then they taught it out of us.
Yeah, exactly right.
Um, yeah. Wow. Well, this has
I'm
been
gonna
exciting. Mm-mm.
good. I'm glad I'm gonna go one step further here and I'm gonna finish off her circle.
Mm.
So how's that? Because I'm sure that's what she has in mind, right?
Yeah.
She's
Yeah.
gonna she's gonna put those she's gonna put those little itchy lines everywhere. And she did put her arrows in a kind of circular mode here. They match that oval. And yet she extended lines out here and got sloppy on her extensions. So it's, she didn't round the
Ah,
edges,
right.
but it looks like we could go through and I could, and I will just go for the heck of it here. Let's go for, I'll do another one here. And I think that I'll make that bigger. And then we'll duplicate it. Go for another one here. I don't know how many she was planning. How many did we put around here, Richard, to help her finish her?
Oh,
We should put probably 12. No.
yeah, almost.
Well,
Well,
th-
she's actually doing she's doing 245s, I think.
interesting.
Or no, she's actually doing less than that because
Yeah, she's saying 90 minus pi over here, or phi. I think that's phi.
so those must be 30-degree angles, 30, 30, 30 in each one of those perpendiculars. So that's three. Three in that one is
I'm just putting in a number over here.
yeah,
I can change it later, but I'm just duplicating and trying to meet her. Something like that, right? To go around to
yeah.
make a sphere. Yeah. Cool. I love the Trinity and the 12 Apostles, Richard. I'm not going to be able to sleep tonight. I'm going to be so excited about that.
Yeah, that's pretty neat.
Yeah. And
Uh,
in the circle we use a 60 metric. So we have 360 degrees. And you said
right.
30 degrees. So 30 degrees goes into 360 degrees. That's where you came up with the 12,
Comes up with 12.
right?
Yeah. Yeah.
Yeah, comes up with 12. And 30 degrees is half of 60.
Right.
And anyway, now
A half of 60 and a third of 90.
yeah, a third of 90. Okay, sir. All
Love it.
right. Any other ideas?
No, it would be overload.
It'd be overload. So we want to do takeaways. I'll give you my takeaways. I'm taking away the Trinity and the 12 apostles. That's what I'm taking away. And I'm taking away that if we take 360 degrees and divide it by 30, we get 12, which
Yeah.
is interesting. And I wonder how the 30 degrees relates to my 12 apostles. So that's what I'm going to be dreaming about tonight. So, how about you? What you got any takeaways other than what you've already shared?
No,
Summarize.
not really. I mean, the main was being able to insert the observer into the observe, which I feel good about that what we've done. And then coming back to our final discussion and being reaffirmed, if you want, about the constructional makeup of a three-pole uh, tetrahedron stretched out to become a circle with four poles in between the three. So you end up with a total of 15. So
Oh,
which is what you've done is said, okay, 3 plus 12.
yeah.
and and again the image of the Trinity comes right back to Bucky's Tetrascroll and um, the Goldilocks and the Three Bears story that he was telling his daughter Allegra, and used the three bears as the Trinity, with the observer on Earth, I guess, surface, being the fourth. And that was his, I think that was one of his ways of trying to say, if you don't have the observer, you don't have the Trinity.
Yeah.
Um, or if the Trinity is there, no one's aware of it because
Yeah, because nobody's observing it. Yeah.
nobody's observing
Yeah.
it.
And so I got something out of that, Richard. When I took your D and moved it outside of the structure and then had D relate back to the structure, I had to create an edge between D and the structure, which created another structure.
Mhm.
There's no way to leave the observer out of the structure.
Right.
And if I'm outside the structure looking in, I'm not seeing all of the structure. The only way to see all the structure is to be in the middle of the structure or
Mhm.
inside the structure somewhere.
In-
And then I have a perspective of all of it.
yeah.
And what it showed me that it's impossible to be outside the structure without creating a brand new structure. The observer has that energy connection to whatever
Yeah.
nodes. And immediately I've created another tetrahedron or some other structure
Yeah. It's almost
or
like D,
another.
the observer won't allow you to separate them. Um,
Right. That D
it's,
is the creator of this structure
yeah.
just by observing it.
Yeah. Yeah.
Just like with the Trinity, with the three bears, there's no Trinity if you don't have an observer looking up into the sky.
Yeah.
And
And
if
that
there is a
goes,
Trinity, it doesn't make any difference.
yeah. Which goes back to that statement that I'm now more and more comfortable in using of unity is not one, it's minimum two, it's plural, minimum two. And then, as he seemed to sort of say, if you've got self, um, self has to have awareness of something. And in
Of
order to have
something.
awareness, there has to be otherness of some kind. And then he reversed it and said, no otherness, no awareness, no self.
Right. And as soon as I have awareness, I have an edge.
And yeah,
As soon as I
right,
have awareness, I have an edge. I have
right.
that. I'll tell you, I just saw a video that I posted on the WhatsApp of Stephen Wolfram,
Mm,
and his whole thing is edges. His whole thing is nodes and edges and computational reality
right.
in relationship to the nodes.
Yeah.
Their awareness is a computation. That is the
Mm,
awareness. If I
yeah.
don't compute, I'm not becoming aware. And as
Yeah.
soon as I become aware, I've just computed.
I've computed. Yeah. Wow.
Yeah. Wow.
Uh,
Beautiful. Okay.
yeah.
I will send you the link to this recording. If you care to share it, I'll send you the graphic as well. And we might tell everybody we had a great discussion, maybe show them the graphic, and
Yeah.
because the topic is angular topology, and we just took those diagrams and went crazy with them.
Yeah. Yeah. We
So
we we stayed on topic or stayed in the chapter. Yeah.
yeah, we did.
Yeah.
Well, my extreme pleasure. Thank you
Well,
so much,
mine
Richard.
too. Yeah. This has been great.
Fun having you in my life. All right, sir. See you next week.
Yeah. Bye now.
Bye bye.